In this video, I want to discuss three properties of logarithms that are useful for rearranging exponential and logarithmic equations and for solving them. And so sometimes we have a variable that is stuck within a logarithmic function. For example, that y, if that was the only unknown, and this said something like log base 3 of 5y was equal to some number, then we have to find a way to be able to eliminate y or isolate y in this equation. And so there is this property that if you are taking the log of an argument that is a product, x times y in this case, then it's possible to separate those two factors into separate logarithms as long as you keep the base the same and you add the two individual logarithms. Sort of like adding exponents when you are raising bases to the exponents of the same base. So there's also a quotient rule. So instead of a product like we have here, we have a division. So we have a quotient. And if you have a quotient and you need to split up these two numbers within that quotient, then you can write them as separate logarithms. Remember, same base all the time. And instead of an addition of these two individual logarithms, we have a subtraction of those two logarithms. And the third one is the power rule for logarithms, which tells us that if our argument is raised to a power, and we need to solve just for x, perhaps, then we can also move that power as a coefficient in front of the logarithm, as you see here, and multiply it by log base b of x now to the 1. And sometimes we have to put it back the other way as well to get the coefficient 1 in front of the logarithm before rearranging. So let's see a few examples. Expand using the properties of logarithms. So the property of logarithm, this one would be the product rule. We can expand it into a sum of logarithms, both base 3. And, well, I need to factor the 12, and there are different factors of 12, so I'm just going to use 6 times 2. So if log base 3 of 6 times 2, all right? Or maybe we'll write it without the multiplication sign. I don't want it to look like an x. 6 times 2. All right, we do have two separate factors now. That's like our x and y in the formula. So this can be written as log base 3 of 6 plus log base 3 of 2. We've just factored the 12. I could have used 4 and 3 as well, or 12 and 1. Here's a quotient. Well, when you have a quotient, instead of having a sum of logs, then you have a difference of logs. So this one will be log base 8 of the numerator, subtract log base 8 of the denominator. Okay, so this difference, or this quotient implies the difference. This product implies the sum. That's the relationship there. Let's take a look at this one, which is going to apply the power rule. We have an exponent on the argument of 5. So this can also be written with the 5 as the coefficient of the logarithm. So this is equal to 5 log base 2 of x now to the 1. This is a very useful one because then if this was equal to some other number, now 5 is just multiplied by log base 2 of x. So it can be divided to the other side and to isolate log base 2 of x. How about this one? We have a product in the numerator, then we have a quotient. So it's a combination of a sum and difference of different logarithms, all base 6. For the numerator, log base 6 of x plus log base 6 of y. And now we better subtract log base 6 of z for the quotient. Sometimes we have to go in the other direction, okay? I have expanded these single logarithms into a sum and or difference of logs. And notice something about all of them. They all had a coefficient of 1 before I started. You can only do this expansion when the coefficient is a 1 in front. So if not, you have to divide by whatever that coefficient is first before you start expanding. Okay, so let's see. We have coefficient 1 here, we have coefficient 1 here, so that's okay. And we have same base. So because this says sum, when we're putting it back into a single logarithm, it will be equal to log base 4 of 2 times 8, which is log base 4 of 16. All right, we multiply the two arguments. When we have a difference, we are going to have a quotient, right? They're both log base 3, so it's something important to check. Don't combine them if they're not the same base. It doesn't work. So we have a single log base 3 of, we'll take this argument, 20, put it over 5. That is log base 3 of 4. How about this one? Before we combine them, we have to have leading coefficients, 1 or negative 1. Here I have a 1. I do not have it here. So where else can this 2 go? So that I have a coefficient 1. Well, remember, we have brought it from here over here, so it can go back also. So this is actually equal to log base 4 of 3 plus log base 4 of x squared. Now they're both leading coefficient 1, and so they can be combined. They'll be combined by making a product of the two arguments because we have a sum in between. Log base 4 of 3 times x squared. Here's a complicated one right here. Remember, leading coefficient 1 before we combine. That's got a 1. This one doesn't. We'll have to deal with that 3. This one doesn't. We'll have to deal with that 4. So, log base 5 of 2 plus log base 5 of x cubed, right? So that goes back up here, minus log base 5 of y to the 4. Now they're all leading coefficient 1. And if I deal with just these two first, we have a sum. A sum means I can combine them to a single logarithm base 5 if I do a product of 2 times x cubed. So it will be log base 5 of 2x cubed. And we still got to do minus log base 5 of y to the 4. And when we have a subtraction, we can combine them into a single log by taking the quotient of the two arguments. So that is log base 5 of 2x cubed over y to the 4. So that's how the properties of logarithms are used, and it will be useful when you are solving equations to know these properties of logarithms.